Right, hi folk. It's been a while since I've done some new chemistry videos. There are lots on my YouTube channel and they all pertain to the old spec, although they're generally pretty good in terms of how they cover the stuff for the new spec as well. But I thought I'd start the process of updating these, and I'll start with what current year 12 are doing, and that's enthalpy changes in developing fuels. So this is something that often looks a lot harder than it really is, because the maths is quite simple. It's just getting a feel for Hess's law. Okay, so we're going to start with a black pen, I think, and we'll be talking about enthalpy changes. Okay, first of all, I'm just going to recap on some of the enthalpy changes that you're expected to be able to identify and use. The first one is delta H. Remember, delta means change. That's the Greek letter. H for enthalpy change, for enthalpy. C, in this case, for combustion. And if you see this little hat thingy here, circle with a line through it, that's at standard conditions. So this would be for something like this reaction. Plus O2 gives you CO2 plus H2. Okay, we need to make the equation balance, of course. So we're going to need 2 there, and we're going to need 2 there. This is a standard condition, so that would be a gas, that would be a gas, that would be a gas, and that would also be a liquid at standard conditions. So this standard conditions thing is important. So just put this up here. So standard conditions, you're looking at 298. That doesn't really see it, is it? That's I'm jumping ahead to the Kelvin there. 298 Kelvin. 1 atmosphere of pressure. You can do it in kilopascals and things as well if you want as well. And we have some reactions obviously that take place in solutions. So we're looking at a 1 molar solution, or 1 mole per decimeter minus 3 if we want to be a bit more complete. Okay. So that's an enthalpy change of combustion. So we're burning a fuel in oxygen completely, and we're burning 1 mole of it. So these things are always defined per amount of substance, so 1 mole. Another one that you're going to have to use quite a bit is an enthalpy change of formation. So this here would be the standard enthalpy change of formation of methane. So we combustion of methane. Let's do the enthalpy change of formation of methane. So the enthalpy change of formation is when 1 mole of a compound, has to be 1 mole of a compound, is formed from its elements in their standard state at standard conditions. So in this case, carbon is a solid at its standard condition, it's graphite to be precise. Hydrogen is gas, and methane we're producing as a gas. So you have all the elements joining together to make 1 molecule of whatever it is you're making, in this case methane. Okay, so that's standard enthalpy change of formation. In some questions you'll see standard enthalpy change of neutralization. So I'll just put neut there, and that is essentially this reaction. It's H plus aqueous plus OH minus. Aqueous gives you H2O liquid. So it's the enthalpy change when you neutralize a mole of hydrogen ions, essentially. So it doesn't really matter what acid you use, as long as it's a strong acid, you should get the same answer if you do it in terms of per mole of hydrogen ions, remembering some acids have got 2 hydrogen ions in them, like sulfuric acid is H2. Okay, so that enthalpy changes that we're going to have to use. Okay. So let's deal with something that allows us to put it all together. Hess's law. Okay, and Hess's law basically says the overall enthalpy change of a process is independent of the route taken as long as the start and the end conditions are the same when you're comparing different routes. So one route cannot end at 1000 Kelvin and the other route end at 200 Kelvin. That wouldn't be a comparison that you can make because enthalpy changes are temperature dependent. So if we take two things, A plus B, they react together to make C plus D, but we could, for example, turn A and B into X and Y, and we can also turn C and D into the same things, X and Y. If that's delta H1, so that's the thing that we're interested in, and this enthalpy change is delta H2, and that enthalpy change is delta H3. So delta H1 equals delta H2 minus delta H3, because what we've basically done is go round like that. Okay, so we've gone in the direction of delta H2 and we've gone in the opposite direction of delta H3, so that's why we've got this minus sign here. So that's some sort of basic concepts really. Let's look at how you'd apply this to specific types of calculations, and there's really two basic types of calculations you're going to come across, at least at AS. So we're going to deal with using enthalpy changes of combustion to calculate another enthalpy change. So for example, if we wanted to work out what the enthalpy change of formation of methane was, which is the reaction we had on the previous page, like that. Now you can't measure that enthalpy change directly. Okay, that's the enthalpy change of formation of methane. But what we can do is we can burn these two things and we can make CO2 plus H2O, make two of those. And we can burn the methane as well. In order to do this, we'd need to add a couple of moles of oxygen either side. And we've got what we'd call an enthalpy cycle. And these enthalpy changes that we've got here are actually the enthalpy changes of combustion, which we can measure in an experiment. So this enthalpy change here happens to be the enthalpy change of formation of methane is going to equal, and what we're going to do is go round like that. Okay, so it's whatever we need to get down to this first point. So what we're going to do there is burn a mole of carbon. So we've got to have the enthalpy change of combustion of carbon, and then we've got to add on two lots of the enthalpy change of combustion of H2, hydrogen. I'll put some brackets around just to separate it out. So that is this bit going down from the carbon and the hydrogen to the carbon dioxide and the two molecules of water. And then we've got to go up to the methane, and that one we're actually going in the opposite direction of the enthalpy change of combustion of methane. So we need to have a minus sign here because we're going in the opposite direction of this arrow here. So that's going to be delta H combustion methane, which will in itself be a negative value, so this will end up being positive. Okay, and these are all enthalpy changes of combustion. Enthalpy changes of combustion are always negative, and that will give us a value in kilojoules per mole, -1. So that's one type of calculation you might be faced with, using enthalpy changes of combustion to work out other enthalpy changes, because you can measure enthalpy changes of combustion fairly readily, and there's an experiment that you need to know to be able to do that. Okay, the other one is using enthalpy changes of formation, which we've kind of just worked out one of here. Enthalpy changes of formation you can sometimes measure directly, but often you can't. So let's have a reaction. Let's say we wanted to work out the enthalpy change of combustion without having to bother measuring it, of ethane. So we've got that reaction there, so we'll need 3 there, 2 there, and then we've got 4 oxygens there, and we've got 3 more there. That makes 7. We need 3.5 there. Put some symbols in: gas, gas, gas. Standard conditions we're dealing with here, so that's a liquid. And when you've got an enthalpy change of formation calculation, what you've got to imagine is what links these two sides together. Is there elements in their standard state? So we can have carbon, hydrogen, and we've also got oxygen here. So you need to know that hydrogen is H2 in its standard state, oxygen is O2, and carbon is just C, like that. So in this case, going from there to there is the enthalpy change of formation of all of the products, and going from there to there, that's the enthalpy change of formation of all of the reactants. So I label that delta H2, that's delta H3, and this one's going to be delta H1. If we apply Hess's law, delta H1 equals minus delta H2 plus delta H3. So what is delta H2 and delta H3? Well, delta H2 is equal to the enthalpy change of formation of ethane plus 3.5. Okay, so this is an oxygen in its standard state. This is also 3.5 moles of oxygen in its standard state. So we've not actually done anything to the oxygen, so we don't actually need anything else there. That's literally what it is. Delta H2 is the enthalpy change of formation of ethane, and delta H3 equals the enthalpy change of formation of CO2. And because we've got 2 of them, we need to have 2 times that plus the enthalpy change of formation of water, and we're making 3 lots of that. Okay, so assuming we're given these values, you can work out what delta H2 and 3 is, and then bung them in here, change the sign of delta H2, add on delta H3, and there's your answer. Okay, or the other way this one is sometimes written is delta HR, so general enthalpy change of reaction, is the sum, so that big Greek letter sigma there is the sum of the enthalpy changes of formation of the products minus the enthalpy change of formation of the reactants. Okay, and that is kind of how that one is normally summed up. Just make sure you've got a balanced equation when you do this, because if you don't, you'll get it wrong. And sometimes, rather than just working out what the enthalpy change of reaction is, a more common question is you're given the enthalpy change of reaction and you have to find one of the other enthalpy changes, so you have to rearrange the equation a little bit, but that's kind of how it works. And the other one that you might come across is the use of bond enthalpies. Enthalpies. Okay, so this is delta HP, and what we're looking at here is the energy required to break 1 mole of a specific bond. One mole of a specific bond. These are averages normally, because a bond enthalpy, particularly something like carbon-hydrogen or carbon-carbon, well, there's millions of molecules of those bonds in, and each molecule, the bond enthalpy will be slightly different, and within the molecule, one carbon-carbon bond will be slightly different in strength compared to another one, simply because of the environment it's in, and what's nearby will subtly alter the strength of a bond. So they are averages. So when you do bond enthalpy calculations, you frequently don't get a value that's bang on what you might determine experimentally, because of the fact that the bond enthalpies are averages, and you're also talking about something at standard conditions, whereas you might not have measured it at standard conditions. So a couple of things about bond enthalpies. A triple bond is stronger than a double bond, is stronger than a single bond. Okay, so that would be something like carbon-carbon triple is stronger than carbon-carbon double, which is stronger than carbon-carbon single. Although when you go from a single bond to a double bond, it doesn't double in strength, and that's something you come on to later when you look at the nature of a double bond and indeed a triple bond. And small atoms make stronger bonds. Like carbon, for example. The reason why there's so many carbon-based molecules is because carbon's a small atom. It can form 4 covalent bonds, and they're short, strong covalent bonds. So as you get shorter and shorter bonds, they get stronger and stronger, because that pair of electrons, that bonding pair of electrons, is closer to the nucleus, positive nucleus, which is what's attracting those electrons. So they get stronger. But you can use bond enthalpies to calculate an enthalpy change of reaction. So there's lots of ways of calculating the enthalpy changes of reaction. Bond enthalpies are one. So we take the same reaction we had earlier, and I'm just going to draw it out a little bit more fully. This is ethane. So bond enthalpies, what you need to have is both a balanced equation and a good understanding of what bonds you've got in the molecules that you're dealing with. So we do this 2 and 3. So the way you can imagine this is that you break all the bonds and you turn it into individual carbon atoms, in this case 2, individual oxygen atoms, that would be 7 oxygen atoms, and individual hydrogen atoms, that would be 6 hydrogen atoms. And you do the same for the products as well. So you smash it into individual atoms, and this is just another application of Hess's law, because we can imagine that the enthalpy change we're interested in is exactly the same as going round there. So that's delta H reaction we're interested in. But what we've got to do is work out what this enthalpy change here is and that enthalpy change there is. So delta H1 is all about breaking bonds. Breaking bonds is endothermic. Okay, and in this case, what we're doing is we're breaking the enthalpy change for a bond between carbon-carbon. So we're breaking this bond here. We're breaking 6 lots of the bond enthalpy between carbon-hydrogen, and we're breaking 3.5 times the bond enthalpy in an oxygen molecule. So we can think of an oxygen molecule as like that. So this here is delta H1. So we'd need to know all these bond enthalpies and work out what these are to work out delta H1. Delta H2 is making bonds, so making a compound or compounds, and that's exothermic. So we're actually going in the opposite direction of the bond enthalpies. So delta H2 will be negative and delta H1 will be positive. Okay, so this will be delta H, the carbon oxygen double. So we need to know that CO2 is this molecule here. So we've got 2 of them. We've actually got 4 of those bonds, plus water, which of course is a bent molecule, like that. So we've got 3 times delta H B. So it's those added together, and this will be negative, and this one here will be positive, and you add them together to get delta HR. So another way that this is sometimes written is delta HR is going to be some of the delta H bonds of the reactants minus the sum of the enthalpy changes of the bonds for the products. Okay, but the key thing is you've got to have a balanced equation, and you've got to look at the structure of the molecules you've got, because you've got to count up the bonds accurately. And whenever I do this, I would always work out what these terms are separately. So I'd work out what 4 times the carbon-oxygen bond enthalpy is, and then 3 times, 6. Hopefully somebody spotted the deliberate error, because of course we've got 3 of them with 2 bonds in each. 6 times that. Add that all together, write that down as a number, then do the same thing here, and then work it out. And if you're doing this in a question, then you're more likely to get the answer correct, and you'll get credit for part of the calculation that you might have attempted. So they're the key enthalpy type of calculations. I haven't mentioned the one where you have to work out the enthalpy change of combustion from some data. Might cover that in another video. But we'll leave it there for now.